Hello, everybody, and welcome. This is the Prague Seminar for Mathematical Physics, our lovely seminar where we feed our curiosity. And today it's my great pleasure. I can introduce our speaker, Razzaq. I hope pronunciation is closing to the correct one. And he's currently a PhD candidate at the University of Bologna. And he's bringing among us very interesting topic, which you cannot see right now, but I guess it's a topic special for invariants of a special linear supergroups. Yeah. So this is last word from me, and thanks for coming for service.
Okay, thank you everyone for being here, and special thanks to Professor Lucio for giving me this opportunity to speak. I will be talking about invariants of super special linear group, and I will try to divide my talk into pieces. And first of all, I'll describe what is the main theme of invariant theory, and then I will describe some basic facts about our motivating example, which is of course of special linear group, very classical example. And then I will try to describe our results, very recent results about super special linear group, invariants of super special linear group. This is a recent joint work with together my advisor, Professor Ita Fioresi from University of Bologna and Professor Marian from University of Valencia. Okay, so this is actually very recent work. We even didn't announce it yet on the archive, so still it is under progress. I will try not to make any mistake. Okay, so what is invariant theory? So this is a very classical subject which was developed much in the second half of the 19th century. Many big names, including Kelly, Professor David Hilbert, and Emmy Noether, and many other big names, they contributed to this field of mathematics. And the idea is actually very simple. Suppose we have a group that G be a group. And then we have an action of this group on, let's say, Xm. I will write it as K of X. So suppose we have a linear group and then it is acting on a polynomial ring. Then, of course, the question is, what is this? Belongs to X such that all so what is this? This is, of course, all those elements inside this polynomial algebra which are invariant under the action of this group G. Okay, so this is called the invariant subring of this polynomial ring. Now, the first question is, what are the generators of this ring of invariants? Okay, so the first problem. What generated. And if you know the answer to this question, it is called the first fundamental theorem of invariant theory for that group. Okay, so answer, if you know it, then so they call it first fundamental theorem of invariant theory for P. Now, actually, before answering this question, another important question is whether this is finitely generated or not, right? And this was a very, very big question at the end of 19th century. And Sir David Hilbert actually gave a partial answer to this question, and he proved that for some kind of groups which are called reductive groups, this is always the case. For reductive groups, this algebra of invariance is always finitely generated, right? And actually, you know that there is this famous Hilbert basis theorem. Sir David Hilbert actually proved this Hilbert basis theorem while trying to attempt this problem. But then, for the general group, he was not sure that if you have a non-reductive group, what can you say? Is this ring always finitely generated or not? So this problem is known as 14th problem of Hilbert, or Hilbert 14th problem. And this problem was stood almost for 60 years, and then around 1960, there was a Japanese mathematician who actually gave a counterexample for this problem. So there are groups for which this ring of invariants is actually not finitely generated. Okay. And then, if you know this, if you know the answer to the first question, the second question is, can you describe Ax of G in terms of generators and relations? So can you, if you know the answer to this problem, then of course the second question is, can you find some relations which completely characterize this ring of invariants? And if you know the answer to this question, then it is called second fundamental theorem of invariant theory. Okay, so this is the main theme of the invariant theory. You pick a group, linear group, you act on this polynomial ring, and then you try to find the answer to these questions. What are generators, and how can you describe this in terms of generators and relations? Okay. Now we will see an example which is of course the motivating example for us. Take G to be the special linear group. Okay, and then the action is this thing. We act on it on this thing which is algebra of polynomials on so this is the algebra of polynomials on n by m matrices, and we have this action of S and n. I will write this again like this. K n times n. So this is the algebra of polynomials on n by n matrices. And how this action is defined, very simple. We take any S belongs to this thing, and the action of any G belongs to this on any matrix, it is defined simply by D. So for any matrix, we first shift it using this any element of SLN, and then we apply that. This is our action. Now, what are the answers to these questions? Example. If we look at it, the simplest and most natural example is determinants, right? Because we know that determinant of AB is equal to determinant of A times determinant of B. So all the n and here, because the determinant of any element here is 1. So all the minors, n by n minors, they are going to be invariant, right? So all maximal minors, by maximal I mean n by n. All maximal minors are invariants. Right? But there is something more. I mean, there is something more to this statement. So, first fundamental theorem of invariant theory for SNN, and it says that actually these maximal minors are all the invariants. It means that this ring is actually generated by all the n by n minors, and I will denote them by the I1, I10. Whereby, okay, by this I mean determinant of x1, yeah, x1 I1, x1 IN, x and I1, x and IN.
But what happens if M is less than N?
I mean m is greater than n.
But there is first fundamental theory for that covered the case N wasn't true as well.
Sorry.
I would guess that there is a theorem analogous result for N less than N. Probably.
Perhaps, but okay, for the moment, I mean m is greater than n. But perhaps you are right. Okay. Okay, let me stick with the notation. M is greater than n. Okay, so this is first fundamental theorem for SNN. So we have generators. Now, what is the answer to our second question? What are the relations? Fundamental theorem of invariant theory for SNN. And it says that this subring EI1, EIN generated by these maximal minors, this is isomorphic to AX I1 IN quotiented by this ideal, where I is generated by where I is generated by these relations x I1 up to in minus 1 x and jn x p1 jn skipped and jn plus 1. Here by this symbol I mean that I have skipped jn from here and I put it here. And here n is from 1 to n plus 1. And then the special name to these relations, these are known as group relations. Okay, so we can completely describe our ring of invariants in this setting using group relations. And why we call it Fluker relations? Maybe this setting is not very familiar to you, this algebraic setting. So let me explain why this Fluker here. You know, so most of us is familiar with this notation. So we have this embedding I of Grassmannian, okay, and B where B is an n-dimensional space to the projectivization of the nth exterior power of V. So let me recall to you what is a Grassmannian. So if we have an n-dimensional space V, then by Grassmannian of n, V will mean all n-dimensional subspaces of our vector space V, right? So if you have a Grassmann, these are manifold, so you can embed these Grassmannians into this projectivization of the nth exterior power of our vector space V. And this embedding works like this. So any space here is actually an n-dimensional subspace, so it is spanned by some basis V1 up to Vn, and then you map it to the class of the vector. Very simple. And in fact, this is an embedding. And it is called Fluker embedding. And then, of course, here we have wedge product. So the coefficients of the wedge products are actually these minors, right? So here, the image of P is, sorry, I, embedding I inside this space. This is actually characterized by proliferation. So Grassmannians as projective varieties, they are characterized by proliferations. So this is agreement. Actually, if you observe what we are doing here is we are doing the same thing, but in terms of algebraic things, right? Here, this action actually we are taking the quotient of n by n matrices using this action of special linear group, which is actually giving us the Grassmannian, and then that is the reason this invariant ring coincides with this this algebra function of Grassmannian. Anyway, so that's it.
Can I ask? So I might miss something, but how Grassmannians come into the game when in our case?
So these are n by n matrices. And you take the quotient of this by SLN with this action.
Mm-hmm.
So when you are multiplying by a element of SLN, you are actually changing the basis of your space, right?
Mhm.
So we are taking all the possible, and so the quotient
Yeah.
actually coincides with the Grassmannian. So it means if you take the polynomial ring on matrices and then you take those functions which are invariant under this action, then they should coincide.
So it does apply just to the special case when you're dealing with G to B special linear groups.
No. Actually, this is something very general. But at the time of classical invariant theory, this approach was not very much active. I mean, this is called geometric invariant theory, and nowadays it is after the modern algebraic geometry. This approach is very useful. And now this is actually this approach was. This approach gained much attention of some mathematician, I forget his name, and the people in invariant theory, they say that he actually gave a new life to invariant theory, because after David Hilbert, the idea of invariant theory was not very active. And then after geometric invariant theory, nowadays it is very active.
Thank you.
Anyway, so now this is just very basic thing. First, we try to see what is the main theme of invariant theory, and then we see an example of special linear group, and we found that yes, for special linear group we have answers to both of these questions. And now this was our motivating example. Now the next question which actually we was interested is this thing. What is a super analog of these directions? So before I describe our results, I'm not sure if every one of us know some basic terms in supergeometry. So I will try to speak about some basic terms in supergeometry so that every one of us is on the same board. Okay. So some basic definitions. A supervector space is a Z2 graded vector space. So, actually, the idea of supergeometry came from physics after the idea of supersymmetry. But today we will not say anything about physics. So we will only try to describe some mathematical terms. So a supervector space is a Z2 graded vector space V, which we consider as the direct sum of two of its subspaces. This is called even part. This is called odd part. And then So each even so we assign to each element. So before this, let me say something else. So the dimension of a super vector space is denoted by P bar Q, where P is the dimension of even part and Q is the dimension of odd part. And then, so these are our objects inside the category of super vector spaces, and then the morphisms. These are parity preserving linear maps. Sorry. Okay. Parity preserving linear maps. I mean, so we consider those linear maps which send even elements to even elements and odd elements to odd elements. And then to each homogeneous elements, we assign a number 0 or 1 depending upon whether it is even or odd. For the even or the odd. And then there is this monoidal structure on this category. So if we have two vector space, super vector spaces V and V prime, then the even part of their tensor product, this is the even part of V times the even part of V prime. The next sum is the odd part of V times the odd part of V times the odd part of V prime. And then the odd part of this tensor product is even part of V times the odd part of V prime plus odd part of V times the even part of V prime. Okay. And then by a super algebra, we need a super vector space A together with a multiplication multiple. So A tensor A to A. And we say that it is super commutative if xy is equal to -1 times parity of x times parity of y, yx for all homogeneous x and y belongs to A. So here, if you have two even vectors, their product is going to be commute, and if you have two odd vectors, their product is going to be anti-commute. And if you have one even one odd, they are going to be commute. So this is called actually super commutativity, but whenever we say super algebra, for this talk we always do super commutative super algebra. Okay, let me see if I need some. Yeah. Okay, similarly, you can define the notion of super modules over a super algebra. So it is going to be a super vector space together with an action of super algebra with the usual properties. And then we denote by this thing APQ. This is defined like A times A by Q, where A is discrete. So where A is the superalgebra over discrete A, and by this symbol Kp by Q, I mean P copies of K and then Q copies of K, where P copies of K are even part of this super vector space, and Q copies of K are all part of this vector space. And by this definition of our super tensor product, it is going to be equal to A naught times A naught direct sum with A1, A1. This is going to be the even part of this, and then we have A1, A naught direct sum with A naught, A1. And then we say that module over A is free if it is isomorphic to AP by Q for some P and Q. Sorry for this boring introduction, but the fun part will be coming soon. So, and a module N is said to be free if M is isomorphic to A P bar Q for some P and Q, which is of course, if you look at this, it means that there exist basis E1 up to EP, and for basis E1 EQ of M such that the even part of M is 10 over A naught E1 up to EP, direct sum is 10 over A1 epsilon 1 epsilon Q, and the odd part is going to be spent over A1 E1 up to EP, direct sum is spent over A naught. Okay, perfect. So now we are almost there, and now similar to the classical linear algebra, now if we have a linear map between two free modules, that P is equal to is SB the linear band between then if you fix a basis on both sides, we get a matrix. And this matrix, if you look at these things, have a special structure, which is a 2 by 2 block structure. Fixing a basis on both sides gives us a matrix like this. E1, E2, E3, E4. It is going to give us a block matrix where E1 will contain E1 entries, T2 will contain odd entries, T3 will contain odd entries, and T4 will contain T1 entries, where T1 and T4 contain T1 entries and T2 and T3 contain odd entries. These matrices are called super matrices. These are called actually even super matrices. Now, very similar to the classical case, in the classical setting, we have the notion of determinant. In the supergeometry, there's analogous notion which is called Berezinian. So, if we have a super matrix T, then its Berezinian is defined. Sorry, our T should be known to DL AP by U. I mean, it should be an invertible linear transformation. Then Berezinian of T is defined as determinant of T4 inverse times the determinant of T1 minus T2 T4 inverse T3. Now, here is a difference with the classical setting. In the classical setting, we have the notion of determinant, which is defined for every linear transformation. It doesn't depend whether it is invertible or not. But in supergeometry, the notion of Berezinian, which is analogous to determinant, it is defined only for invertible linear transformation. So we define only for even supermatrix, invertible even supermatrices. Now, if we look at this definition, then this is saying that T4 should be invertible, right? But there is a theorem which tells us that if your even supermatrix, if it is invertible, then T1 and T4, both of these things are invertible. So actually, there is an equivalent definition of it, which is actually determinant of T1 inverse times the determinant of T3, sorry, T4 minus T3, T1 inverse T2. So for invertible matrices, one can actually prove that these two definitions are equal. And there is another theorem which tells us that this map, the Berezinian from invertible even supermatrices to the non-zero even part of our algebra A, this is a homomorphism. Homomorphism, in particular, it is multiplicative. So Berezinian of is AB is equal to Berezinian of A times Berezinian of B. So it shares this property with the determinant in the classical section. Okay. Now we have enough things, almost enough things to describe our results.
Typically, we're dealing with models, things like that, right? So there's this idea in the invariance basics number properties that we should ask for the ring to be able to define even three modules. So, you know, the number of, let's say, basis elements for the module then is fixed. So here with super algebras, is it clear that you have this IBM property?
Can you please repeat the question? I didn't get it.
Yeah, so typically in order to define three module and rank of three module, which is you know, some basis of fixed size, you need to see that your ring over which you define this module satisfies invariance basis number properties.
I'm not sure about it. I look at it, but at the moment I'm not.
Usually it's algebra functions from supermanifold which has this property. I think that's the why we have it.
Sorry?
I was just saying that usually in supergeometry, for example, A is, for example, algebra of functions on a supermanifold, which has this property Romanov's asking this invariant triangle can define what is a super rank of the module invariant.
So now, again, let us go back to our questions, which we write at the beginning. So now, again, we have this thing that x1, let's say x1, x1, p, x r1, x r3, alpha 1 head, alpha 1 q head, alpha r1 head, alpha r q head, beta 1 s1, beta 1 s e, beta s1, beta s3, and have y 1 head, y 1 head, 2 head, y s head, 1 head, y s head. Now, suppose we have this thing, and then we have this action of special linear group on A, and then actually I will write it like this: M R S times P plus Q. And the action is same that we defined for special linear group. Now, can we say something about invariants and fluctuations? Can we describe, first of all, can we describe invariants? And then if yes, can we describe fluctuations, super fluctuations that describe this being of invariants? Now, in the classical setting, we actually saw that for classical setting, the invariants are going to be maximal minors, which are defined by determinants. Now here, as an analogous result, one should consider the notion of Berezinians, right? Maximal Berezinians, because we know that Berezinian is a homomorphism. So if we multiply by something which is of Berezinian 1, then it is going to be sorry.
Yeah, so what's the definition of a cell A PQ? So you require the Berezinian leaf, which one?
Yeah, Berezinian equal to 1 of our algebra. But the problem here is that Berezinian doesn't live inside this thing, right? Because of this definition that we have this inverse determinant of T4 inverse, and if we want to use that, the definition determinant of T1 inverse. So what should we do? We modify our setting just a bit. We took the localization of this thing at DI1, DI R, and DJ1 head, DJS head. So we took all the determinants here. So we make them invertible using so we put this thing by hand. So we make them somehow invertible, or you can say we are just focusing our attention to those points of the Grassmannian where every Berezinian is defined, right? So this property was lacking, but now we take this localization, so we put the property by hand, and now with this modified setting, we get this first fundamental theorem. But sorry, actually, before talking about first fundamental theorem, I have to introduce the notion of super Cramer rule, which is actually not very familiar, but we use it, so I have to explain. So classically, we know that if we have an invertible matrix M, and here we have some unknown vector X, and here we have some vector D, then what are the solution to this equation? 1. So then the solution to this equation are xi is equal to determinant of MIB divided by determinant of N. Right? This is Cramer rule in the classical setting. Now, what is Cramer rule in the super setting? So if we have an invertible even supermatrix M, and we have this equation, then the super Cramer rule is this thing. Instead of determinant here, the natural thing is to consider Berezinians, and yes, this is the case. So Xi's, the first even entries of this X, they are going to be defined by Berezinian of MIB divided by Berezinian of M. And then the odd entries, they are going to be defined by Berezinian star MJ of B divided by Berezinian star of N. The Berezinian star of a matrix T1, T2, T3, T4, we mean the Berezinian where we switch these things. So T4 is switched by T1, and T2 and T3 are switched. This is super Cramer rule. Actually, here we use something which is not very, standard. The standard super matrices looks like this. These are super matrices, even super matrices, where here we have even entries, here we have even entries, here we have odd entries, and here we have odd entries. But here you saw that if we have an even vector here, then these things are okay. we put at the even positions, we put even vectors, okay. But here we are putting an even vector at an odd position, right? So this is something, no, I mean, not very much, I mean, popular in supergeometry, but yes, this has to be used because otherwise Bayesian is always even things. So when we put an odd vector at an even position or an even vector at an odd position, we get the Bayesian which is odd, and so in detail, these are called Rome supermatrices. Okay, now with this definition of Rome supermatrices, we actually get this first fundamental theorem for SLAPQ, and it says that the ring of invariants in this, let me call this thing as, let's say, O hat, and says SLAPQ is generated by super minus and say super minus. And okay, so in this result, the main key is actually this super camera. And I'm not, because I'm not sure how much time is left.
We started around 5 minutes ago, so 5 minutes left.
5 minutes.
But just to assume your rest of the talk to your
Okay.
needs.
Okay, so I try to be a bit fast. Okay. So now whenever we generalize something from classical geometry or any classical subject to some general thing, what we always do is try to look at the classical thing again and try to see if something is there that we could generalize. So now if we look at the classical Fluke relations, for example, if I look at Grassmann 2,4, then in this case, the classical Fluke relation is x1 to x3 4 minus x1 3 x2 4 plus x1 4 x2 3 is equal to 0. Right, this is the only Fluke relation in this case. Now, if I look at it directly and try to see what will happen in general, it is almost impossible to figure out what will happen in the super setting. So then we get this idea that actually, if you look at it, I can write it like this: x1 to x3 4 is equal to determinant of x1 3, x1 4, x2 3, x2 4. This is equivalent. Right? Now, if this is true, then I can say something about, I can guess something about super. Maybe I can say, okay, here I put super Bayesians and then it is equal to Bayesian of some matrix which contains the Bayesian. Right? So these are Fluker coordinates is equal to determinant of a matrix which contains Fluker coordinates. So, but this is just for this example. Now the first question is it true in general? Can I always write a classical Klug correlation in this form as a product where the product of Klug coordinates is equal to the determinant of some matrix which contains Klug coordinates? The answer is yes. We can always do this. And now, because I don't have enough time to explain how we can do it, but yes, we can do it. And the key here is, which is something called Jacobi's complementary minor theorem. So there is something in linear algebra called Jacobi's complementary minor theorem. You can use it in some way, and you can produce Klug correlations from it, and they will appear like this. Okay. So it means yes, there is a chance that we can generalize this notion to super geometry using this trick. And then what we did actually in the next step, we try to prove a super version of the Jacobi's complementary minor theorem. Sorry? Okay. So this is actually equal to, okay. If we have an invertible matrix A belongs to the linear group, then you fix U from last R rows and first R columns. These are just indices, and then V tilde is, so U tilde is actually 1 up to n minus V, and V tilde is 1 up to n minus U V. So these are just the complements of this set of indices. Then this Jacobi complementary minor theorem says that determinant of A U V is actually equal to determinant of A times determinant of A inverse V tilde U tilde. Yes, whereby this angle AUV, I mean from A we delete all the rows in U and columns in V. So we delete all last R rows and first R columns. This is this, and here we have V tilde and U tilde. So we have to delete first R rows and last R columns. So then we can use this identity somehow. There is a small trick here, and then from this identity we can produce all the correlations in this form. Once we have this statement, then we actually prove a super version of this identity. Super therefore is complementary minor theorem. So here actually there should be a sign -1 raised to the power r times n plus 1. Here for these, for generating our Klug correlations, we actually fix these indices, but this identity holds for general set of ordered indices, and then this power depends on the coefficient on the indices we choose here. So we try to prove super Jacobi's complementary minor theorem, and it is very similar to this identity. Here, instead of determinant, we have there is linear, and here I have some other sign. And then we play the same trick with this super Jacobi's complementary minor theorem that we played here to get the classical Klug correlation, to get the super Klug correlation. And because I don't have time to explain the strategy, what we did, but let me directly write what we get. So X I mu hat X J mu hat it is going to be equal to the variance of X J mu hat X mu hat X star I J and X star I mu hat. And similarly, we have X I mu hat X lambda hat mu hat, and it is very similar to this thing. And then we also for X star I mu hat X star J. And again, this is very similar to this thing. So if you look at it, it is very similar to this thing, that the product of two classical Fluker coordinates, this is equal to the determinant of some matrix which contains Fluker coordinates. And here in the supersetting, we get a similar thing for super Fluker coordinates. So the product of two super Fluker coordinates is given in terms of the Berezinian of super Fluker coordinates. Actually, this is the result for SL11. We also have for SLRS, SLMN, but I mean they appear very similar to this. That here you have you have a product of super Fluker coordinates, and then there is a big matrix where you compute the Berezinian. So okay, that's it. Thank you very much.
Thank you for here comes the time for your questions.
So maybe an obvious question, is there a significant relation with this super relations in the classificity?
So because here we actually take this localization, so you can think of it like this. That these are the relations which characterize an open set of super Grassmannian as a supergrid. Actually, this is a dense subset of the super Grassmannian. So, for example, if you look at just the classical Grassmannian, then all those points of the Grassmannian for which every Fluker coordinate is invertible. At some point, I heard the talk, and the speaker was telling that there is a special name for this open set, and it is called the main stratum of the Grassmannian. I'm not sure if it is. So here we are doing the same because due to this property that we cannot define Berezinian everywhere, we are fixing our attention to only those points where everything is defined.
So like you said it, but what are fake superminors?
Yeah, fake superminors is so okay. I think I erased the definition of super matrices. In the definition of super matrices, we saw that we have this block where M1 and M4 they contain even entries, and M2 and M3 they contain odd entries. But now, if you look at this super Kramer rule, if, for example, if B is an even vector, this is an even super matrix, then here we are actually putting this vector B at an odd position, right? So these type of matrices, they are called fake super matrices. So the super minors coming from these type of matrices, we call them fake super matrices.
So also in the classical setting, determinants are characterized as a determinant is characterized as the unique anti-symmetric function or isomorphic subject to a normalization condition that is equals to 1. So In the classical setting, determinants are characterized as unique and asymmetric functions of rows of a matrix
Yeah.
subject to normalization condition. So is that also the case for Berezinians?
Yes. There is actually, I am not sure if this is the origin of the definition of Berezinian. I think the origin of the definition of Berezinian comes from integration over supermanifold, if I am right. But you can define it like this. Axiomatically, you can define Berezinian like this. That these are functions which are homogeneous of degree 1 in even rows and homogeneous of degree -1 in odd rows. Similarly for columns. Yes, that's it.
Any other question?
Yes, maybe I can ask a quick question.
Yeah, sure.
Okay, I was wondering if you thought of the quantum case. Yeah, so can you say something about quantum groups, for example, SLQ2 acting on the quantum plane? What are the invariants there?
Hi, Thomas. Are you asking classical case or the super case?
I mean, both are interesting. If you can say something about one, I'm happy.
Yes, about the classical case, yes, there are works you can find. For example, there is an article, an old article by Rita Fioresi, and she actually computed it, the quantum Klug correlations. Yes, done. And also there are some other works. But on the super side, because this is the first time we are looking at the classical super Klug correlations. At the moment, we don't have a quantum thing about it, but we are hopeful that we can get a quantum version of these super Klug correlations too.
Interesting.
Yeah.
Thank you.
Thank you very much. And actually, sorry, this technique that we used here, using the Jacobi's complementary minor theorem, this is also a new technique, at least for us, to look at Klug correlations. So maybe this technique could be useful even for the classical quantum Klug correlations. So we will review those quantum Klug correlations. And we will
Okay.
try to produce them again using this technique that we used here.
In the quantum group case, in the classical, does it matter what the Q is, whether it's like Q or it's root of
I am not sure about exactly the condition, but yes, I think there is some condition in the Rita's work.
Okay, so maybe I have more question. You exposed in a former situation when not this super case has been considered. Actually, two such fundamental theorems. So this the second one you have there. Has it any analogy in what you exposed here, or do you have anything anything to add for the questions of some G invariants of those rings of invariants?
Sorry, I
Or
didn't
maybe-
get your question. Can you please repeat it?
I'm asking whether there is some analogy of the second fundamental theorem you mentioned in this super case. Maybe this is somehow involved in what you've spoken, but I cannot see properly.
I mean, this is second fundamental theorem. So we have the super Klug correlation.
So, so you have here in this case, yeah, maybe I just didn't get this this point because
So,
I
the-
wasn't.
okay, so the first theorem is this one. So
Okay.
this ring of invariants is
Mhm.
identified by superminors and fake superminors.
Mhm,
These are the symbols for superminors and fake superminors.
mhm.
And here I am writing this relation. These are the relations we call supergroup relations. So this is the second theorem for SL11, but yes, we also have it for SLML.
Yeah, sure.
Yeah.
Yeah. Probably hasn't been here, so I.
If you write, you can actually compute this is for SL11, it is very easy. We can actually write it as a polynomial relation. So, very interesting. But if we look directly at the Kluger relation, it is not very easy to guess what will happen. But yes, this strategy is very
Mhm.
useful.
And you said that you can enlarge this set of relation to arbitrary n and r.
Yeah. But then, I mean, then they look very bad because
Mhm.
this matrix is very weak. I mean, it is very difficult to write down.
Okay. Okay. Sorry for my ignorance, not spot the second. Okay.
In the last few minutes, I was very fast. So
Okay. So, any other question? Not the case. Let me ask for a second round of applause.
thank you very much to everyone.
Yeah, thank you. I think we have Carlos or in general.